So we have a circular bar of length 600 mm, and it is supported at its both end. So it's a simply supported bar having a length 600 mm. And speaking of the load, it is acting by an cyclic load at its exact center, which varies from 25 kilonewton to 55 kilonewton. Okay, so the range of force acting at the exact center, I mean cyclic load, is 25 kilonewton to 55 kilonewton. Also, the factor of safety is given as 1.6, surface finish factor, size factor, all that correction factor is given. We have to determine the diameter of the bar. In addition to that, the ultimate strength of the bar is also given, as well as yield strength and endurance strength. So we have to determine, considering all these facts, we have to find out the diameter of the bar. So let's look at the detailed solution. So first, writing all the given condition. I mean the length. It's also tell us 600 mm. Then it's a concentric cyclic load varies from 25 kilonewton to 55 kilonewton. These are the factor of safety. Um, Surface finish factor is termed as, if you know the basic equation, there is a terms called ABC. You can find the data book. Here in this question, the load factor is not given, so I am assuming it to be 1. So whenever the load factor is not given, it's just assume it to be 1. And the surface finish factor B and size factor C is already given. And ultimate strength, yield strength, and endurance strength of this respective circular rod is also given. These are all the given condition. Because this is the simple figure. How does this circular rod look like? It is both supported both and having a central load, cyclic load acting exactly at the center. So we need to find the since we having two range of load, maximum minimum force. Obviously, we have to find the maximum and minimum moment. Okay, bending moment, because it's a bending force. This due to this load, what really happens is there is a bending occurs, bending stress occurs in the circular bar. So obviously, we need to find the maximum and the minimum bending moment. So one thing you have to keep in mind is for a simply supported beam on both end, where the force acting at the exact center among all these points. I mean this point, this middle point, and this among these all 3 point where the maximum bending momentum will be. I mean, if you draw the corresponding bending moment diagram, maximum bending moment will be at the exact center. I mean, where the force act. Okay, what really happens when a force happens, when you apply the force, there will be sagging like this. Okay, this is what really happens. So the maximum bending moment will be the exact center. So we have the, moment, maximum moment as WL by 4. Since the force is acting at the exact center, we need to take this equation at this point only, that is WL by 4. Okay, you can learn like that way also. So to find maximum, so we the general equation we got. So we need to find the maximum bending moment and minimum bending moment for this respective equation. Since we have two load, maximum load, minimum load and maximum load. So to find maximum bending moment, just use simply WL by 4. But W is the weight or the force acting. That is the maximum force you have to substitute. Here it is 58 kilonewton. That has to be converted into Newton. Okay, that bending moment has to be Newton mm force. So in order to get that, you have to convert the kilonewton to Newton. Remaining length, just like same units mm. So just substituting, you get this corresponding value. Same way, you can find the minimum bending moment by substituting the minimum force, that is 25 kilonewton. It also should be converted into Newton. So same, so you get the corresponding minimum bending moment in that case too. So we have the maximum and minimum, M max and M minimum bending moment in this case. And next, the next step is to find the mean bending momentum. So mean, not to find mean bending momentum, just use this formula, M max plus M minimum 2. So you get the mean bending momentum as this value. Okay, we get this value. Then the next step is we have to find the variable bending moment. Okay, so there is not much difference between the equation of mean bending moment and variable bending moment, except the middle part. Okay, here it is positive and here it is negative. So you get the corresponding variable bending momentum. Okay. So next step is we have to find the since we got the variable bending momentum and mean bending momentum, we have to find the corresponding mean bending stress and variable bending stress to substitute in the relation equation, which I will tell later. So to find mean bending stress, let's use mean moment by z, because for the bending moment equation for stress is m by z. Not to find mean bending stress, just use mean moment by z. Z is a section modulus. Could these all equation you can find the data book. You don't need to learn all this. Same way you can find variable bending stress, which is also represented as sigma a or sigma b. Same value, variable moment by z. Okay, we got corresponding mean bending stress and the variable bending stress. Next, we need to use the what type of relation. There is a Goodman relation and Soderman relation can be used to solve this problem. But in this question, they haven't mentioned which relation to use. Okay, in that case, our journal will be solving it by both the Goodman relation and Soderman relation and taking the maximum diameter. That's the way to solve this problem. That's how we do. Okay, so we have so this is a Goodman relation for ductile material. Don't take the equation for brittle material, just take the relation of ductile material. They haven't mentioned it is steel in this question, but even though if it hasn't mentioned any particular material, if it's steel or not, just assume it to be ductile and take the corresponding uh, ductile equation. Okay, so to show you. Okay, so this is the equation for ductile condition, Goodman relation for ductile condition. This is the equation. Here, KTF, stress concentration factor due to fatigue loading, is not given. Because this parameter is not given. If it's not given, let's assume it to be 1. The remaining sigma A alternating stress or variable bending stress, we just have find out. ABC is already given in the question. While A is not given, but we have to assume it to be 1 since it is also not mentioned in the question. Sigma n endurance limit is given, sigma u ultimate stress is given, sigma m this we just find out. So we have all the parameters substituted in the equation. We got the variable stress, bending stress, and mean bending stress in terms of d, and that is our ultimate aim, right? To find d. So substituting this equation, we will get the final equation like d cube is equal to this value, and the value of d will be around 58.6. This is the diameter. Okay, this is d. This is d. Okay, this will be the values. 658.6 mm. Okay, so we got the diameter by applying Goodman relations. So I have to find Soderberg relation. These are the two relations that explain the fatigue loading, fatigue failure. So need to find the diameter by using both the relation. We have to consider equally this both relation and taking the diameter based on the final value. Is the way to solve this type of problem. So next is by using Soderberg relation. This is the corresponding equation for Soderberg relation for ductile materials. Still, I am saying you cannot take the brittle material case. Just you take the ductile material case, even though it is not mentioned steel or ductile case. Just assume to be ductile material. That's the way to solve this type of problem. Where also we don't have stress concentration factor due to fatigue loading. Assume it to be 1. Remaining all factor is we know. The only difference between Soderberg relation and Goodman relation is the term right here. In Soderberg relation, it is yield point stress. On the other case, it is ultimate stress in the case of Gutenberg. Okay. So, sorry, Goodsman relation. So, we got by substituting this equation, by Soderberg relation, the diameter will be around 26 mm or 25.99 mm. So, considering both the values of diameter by both Soderberg and Goodsman relation, you should always take the maximum diameter case because these are all the fatigue failure theories, right? So if you make some material with minimum diameter, we don't know what factor. Maybe you due to it failed due to fatigue loading, Okay, due to considering good man's relation or sort of, so we have to always take the maximum value to be fail safe. So comparing these, the maximum value will be obtained by Goodsman relation, right? So the answer, the maximum diameter you have to take, then the answer, the safe answer to take is by Goodsman relation. Just because the value is higher than Soderbergh. So the diameter will be 58.6 mm. Okay, this is a way to solve this type of problem.